Now we will see the topic loop antenna. Now coming to loop antenna is an uniform wire, and we turn the wire into a loop, right? So that loop, which in turn we will be calling as an loop antenna, and we use that to just radiate the electromagnetic signals through the loop. So consider we have a wire and we try to form a particular shape, mathematical geometrical shapes that we can form, and those will be like the loop antenna. So we have different forms of or different types of loop antennas. For example, we can see in the slide we have a square loop antenna, circular and rectangle, and even you have rhombus, ellipse, right, and trapezoidal. Many loop antennas are present. Right now, basically we see the radiation pattern of loop antennas. Right now, very basically we can see that there are two types of loop antenna called as small loop antenna and large loop antenna. So how we differentiate small loop antenna and large loop antenna is we differentiate based upon the circumference of the loop. Right? If the circumference of the loop is less than lambda by 10, then we call that as small loop antenna. And if it is greater than lambda by 10 or approximately lambda, and then it is called as the large loop antenna. Right? The large loop antennas are called or used for as a resonant antennas. Right? In the small loop antennas, we are going to have like uh, the antennas for radiating the electromagnetic fields as well. Okay. Now we will try to see how we can able to derive the magnetic field equations. That is electrical field and the magnetic field equations of a circular loop antenna. Right now, first initially what we do, we uh, we consider a loop of uh, circular loop of radius small a and circumference of c, and which is as lambda by 5 or lambda by 10, right? So the circumference can lambda by 5 or lambda by 10, and the radius of the loop let be as less than 0.03 lambda, right? So this is electrically small loop which we are taking, and we consider that the current in the loop is as a DC current. It's a constant current. Now, now we are going to modify that loop, the circular loop, into a square form. So we consider, so in order to find out the radiation due to that circular loop, what we just do is that we just take that circumference and we just modify that into a square loop of a b c d of, right, and then we can have the length of the square as d. Right? And now, in order to calculate the radiation, that is electrical field and the magnetic field parameters of this particular circular loop, we go with the spherical coordinate system. So initially we consider the basic of Cartesian coordinate system as x, y, z, and then we so these, right, and being as the center as that is the center as origin, we keep this particular loop at the center. So the center of the square has to meet with the center of the origin, right? And then after this, what we do, we just go with the spherical coordinate system, mentioning the values of et, that is we have like r, theta, phi dimensions. Now we can see that at a particular point P, so we consider a particular point P where that point P is the point of observation of the fields. So we can see that from the field, from this particular ABCD loop, right? So we first find out the electrical field due to AD and then BC, and sum it up, and we will be getting it. Okay, so if you can see the vector directions, it is we are going to take the azimuthal angle phi. So towards the azimuthal angle phi, we have the electrical field component which I derive, and towards the uh, inclination angle, that is theta, right? Zenith angle we call. So we calculate the value of h phi, right? Now, the field component E phi, is, so we can see the field component due to AD plus the field component due to the length BC. So if we see the figure, so we are going to calculate the field component E phi due to the loop AD and then BC. So coming here, so the field component, now we assume that the electrical field due to that is a constant in terms of magnitude and opposite in phase. So due to the AD field component, so we assume that it is as minus E naught into e power j phi by 2, and psi is the phase difference, right? Total phase difference. And similarly plus due to the field component due to BC, so it is as E naught into e power j psi by 2. So if we can just do the mathematical form, so actually we know the formula where e power j theta minus e power minus j theta is sine theta, right? J sine 2j sine theta you get. So we just find it, right? So here e phi we get like minus 2j e naught into sine theta, where theta is your psi by 2, right? Now where psi we can see here, the value of psi is nothing but BD sine theta. This is the phase difference. It's a formula which we have to remember. So this is the form of psi, right? BD sine theta, right? Then E phi we get as minus 2j E naught sine of BD sine theta whole by 2, right? Then due to the individual dipole E naught, so we have like E naught equal to, now actually the previous equation we consider this as one equation, equation 1, and due to the dipole, individual dipole as E naught, so we have a formula where E naught is equal to J 65. Now this is the equation which we got in terms of the value which we got in terms of an half-wave dipole antenna. Similar thing which we are going to just substitute here. Okay, and then if we can substitute this E naught in equation 1, so we have, instead of E naught we just substitute this value J60 pi into IL by lambda E. So if we substitute and then we do the mathematical steps, right? So if we can simplify that, we get E phi equal to 120 pi square into I sin theta into A by lambda square A, where A will be the length, that is the area, that is the length into L into DSA. Okay. Now this is the equation which we have to remember for the electrical field component due to the circular loop. And similarly, for the magnetic field component, we can easily calculate by the relationship of intrinsic impedance with E and H. So this is the formula, this is the relationship we have. So eta equal to E phi by E theta, right? So this is equal to 125. Then we can just calculate, simplify the equation. So H theta equal to, we get H pi I sin theta into A by lambda square into A, right? Amperes per meter. Now this is how we calculate the magnetic field and the electrical field as well. Now we calculate the total power radiated. So the total power radiated, now this is the formula which, this is the equation which we have seen even in the dipole antenna. The same, that is the total power radiated is integral over the surface. It is like power radiated, the average power radiated into ds. So average power radiated is half power of half into E phi into H theta. ds, it will be like sin theta d theta d phi, right? And then if we just substitute, if we do just do the mathematical calculation, we get an equation of W, that is the total power radiated, as 160 pi square, pi power 4 Im square into A by lambda square the whole square. So this is the equation of total power radiated, and from this we can calculate the radiation resistance. So the radiation resistance is W by R square RMS. So we know that the relationship between the R square RMS is like Im by root 2 we get. So if we just do the calculation, then we get the value of P, that is radiation resistance, as um, 31,200 into A by lambda square, the whole square root ohms, right? So this is the formula which we have to remember for the radiation resistance of the circular loop, right? So if it has n turns, if a particular circular loop, if it has only one single turn, then capital N equal to 1 if it has more number of loops, right? So this is the formula which we use. So the radiation resistance of n number of turns, right? So it is equal to 31,200 multiplied by, it is as n into a by lambda square, the whole square in terms of ohms. So this is how we calculate the radiation resistance of the loop antenna with n number of turns, right? And we can go with the applications of loop antenna. Now if you can see the applications of a loop antenna, so these loop antennas are used in our aircraft direction finders. So it is used in aircraft direction finders. So in order to find out the directions, we use this loop antenna. The second point we can see in radio receivers for receiving high frequency waves. So it is used to receive the high frequency waves, right? The third point, it is loop antennas are also used as ultra high frequency transmitters. So in order to have an high frequency transmitter, we use loop antenna, right? And the last point, in RFID devices, so it is used in loop antenna is used in RFID devices to detect the position of the transmitter. So we can use this loop antenna in various applications, right? So hope you enjoyed this video and you got some data or the information on loop antennas. Thank you for listening to this video. Thank you so much.